Hello and welcome. In this video, we are going to talk about continuous functions, one-sided continuity, the continuity of the composition of functions, and we're going to wrap up with the intermediate value theorem. But if you watched the previous video, I encourage you to pause the video and work through this warm-up for part A and B. Hopefully you had time to pause the video and work through this warm-up. For part A, it says, given that f of x is continuous, determine the value of a. Well, we know that if it's continuous, the value that we're interested in is x equals 2, because this first piece of the function is a quadratic, which is continuous everywhere, and the second piece of the function is a line, which is continuous everywhere. So what we're going to do is we're going to substitute 2 in to look at what's happening from the left and the right. So the limit as x approaches 2 from the right would be this top piece that it is when x is greater than 2. If I plug 2 in, I'm going to get 3 of f of x. 3 times 2 squared plus a. 2 squared is 4 times 3 is 12, so this is going to be 12 plus a. So the limit as x approaches 2 from the right is 12 plus a. The limit as x approaches 2 from the left of f of x is going to be what we get if we plug 2 into this piece of the function, which is 2 minus 3, or negative 1. Since we know that it's continuous, we know that the left side should be equivalent to the right side, should be equal to the value of the function, which is what we actually get when we plug it into the second piece. F of 2 is equal to this. So we can say that 12 plus a equals negative 1, and if we subtract 12 from both sides, we get that a is negative 13. So part B is asking us to sketch a graph that is continuous from negative 3 to 2, from the open interval from 2 to 5, and then from 5 to 7. But let's look at these other pieces of information. With a removable discontinuity at x equals 2, which means at x equals 2 there's a hole. That's the only removable discontinuity we have. And a non-removable discontinuity at x equals 5. So that's either going to be a vertical asymptote or a jump. So now, 3, 4, 5. I'm going to just put a little star here so I remember that I need to have some sort of jump discontinuity there. So I'm going to go up closed interval from negative 3 to 2. So I'm going to start here and I'm going to go to this hole. And then from 2 to 5, and that is a closed interval from 2 to 5. Then I'm remembering this little blue star down here means I'm going to have a jump discontinuity. So I'm going to have an open circle. That would be a non-removable discontinuity. And then I'm going to go from 5 to 7. And it is a closed interval on 7. So here's a sample of what this function might look like meeting all of those requirements. So the key things there, removable discontinuity is insinuating we have a hole. Non-removable discontinuity would mean that we're looking at a jump discontinuity, a vertical asymptote, or an oscillation. Let's talk a little bit about one-sided continuity. When we are finding one-sided limits of more complex functions, we need to try and think about what would happen as we get close to the number that we're trying to plug in. But remember, in terms of a one-sided limit, we're not actually plugging in those values. When you're doing this, sometimes it's helpful to sketch a graph of the function. Sometimes it's helpful to just think about a number slightly bigger or slightly smaller than the number that you are plugging in. So let's look at number 1. The limit as x approaches 3 from the right, so something slightly bigger than 3, of this function. So the first thing that I notice is that if I ignore the absolute value here, I'm going to have something over itself, which is going to give me 1, which really means there's 2 things that could happen when I plug in a number here. I could either get positive 1 or I could get negative 1, because I'm dividing something by itself. If it happens to be that the numerator is positive, when I divide something positive by something positive that is the same, I will get positive 1. If the numerator happens to be negative, when I divide that negative number by the positive version of that number, I would get negative 1. So no matter what I'm plugging in right around 3 here, or any number in general, I'm going to either get positive or negative 1. Now, I am plugging in a number slightly bigger than 3 to the right of 3. So you could think of that as 3.1. If I plug in 3.1, I'm going to get 0.1 over 0.1, which is going to be 1. So I'm going to get a positive value because I'm getting something positive over the same thing, also positive. So this limit is going to be equal to 1. Now, number 2 is the same problem, except now we're coming from the left. And if we're coming from the left, this numerator is now going to be negative. And I'm going to divide it by the same exact number in the bottom, but positive. So this limit is going to be equal to -1. So you could think about this just to help your head wrap around what we're doing here. You could plug in 2.9 and see what happens if you plug in 2.9. Now remember, we're not actually being told to plug in 2.9. We're just saying what's happening as we get close to 3 from the left. Okay, number 3, the limit as we approach pi from the right is actually telling us in this piecewise function that we should be plugging it into the piece that is to the right of pi, which would be this piece here. Because everything less than 0 is the bottom piece, everything greater than or equal to 0 is the top piece. Pi is definitely greater than 0. And this is continuous, so really all we have to do here is just substitute pi in. Cosine of pi is -1. So don't let these piecewise functions intimidate you. Just think about which piece is this value close to and what's happening at that value. One-sided limits are going to tell you to plug something in from a particular side, so you don't have to think about what's happening on both sides. All right, let's move on to continuity of compound functions. If we have a function g that is continuous at a c value, and we have a function f that is continuous at the same c value, then the composition of those functions will be continuous at c. Big picture, if we're talking about a composition of functions, think about initially if there are any domain restrictions, then find out what the composition of those functions is, and then identify if we have any domain restrictions in the composition. So for number 4, I know that for f, I'm not allowed to plug in anything less than or equal to 0. So I'm just making that little note to myself. In this function, all of my x values have to be greater than or equal to 0. Otherwise, we would be taking the square root of a negative number, which is not allowed in the real number system. I don't have any domain restrictions at all on g, because g is a line. I can plug in anything I want to that function. Now let's actually figure out what f of g of x is. So if we plug g of x into f, this is going to become the square root of 3 times the quantity x minus 5, which is going to give us the square root of 3x minus 15. Now, any value that was continuous here or here potentially has an issue when we look at this function. But really what we just need to think about is we still need the inside of this function to meet our domain requirements. So what am I allowed to plug in here? I just need to make sure that 3x minus 15 is greater than or equal to 0, which means that x is going to need to be greater than or equal to 5. So we could say that this is continuous on the interval from 5 to infinity. Why don't you go ahead and pause the video and see if you can work through number 5 on your own. Then unpause the video and see how you did. All right, number 5, both f and g are continuous on all real numbers. So let's just jump into finding the composition of these functions. F of g of x would be cosine of x quantity squared. This is continuous everywhere because cosine is continuous everywhere. So this is continuous on the interval from -infinity to infinity. We're going to wrap up this lesson by talking about the intermediate value theorem. Okay, the intermediate value theorem, also known as IVT. I'm going to read it to you and then I'm going to try and help you understand using this graph what it's saying. If f is continuous on the closed interval from a to b and there is some y value k between f of a and f of b, then there is at least one x value c between a and b such that f of c equals k. Now, that is some very complicated verbiage. Let's try and make this a little bit more concrete. Let's give these values. Let's say that a is 1 and b is 6. And then let's say that up here, this output, f of b, let's say this is 10, and let's say that f of a is 2. What this theorem says is that if this is continuous, meaning we never lift up our pencil at all when we are drawing this piece of the function between 1 and 6, then every number between 2 and 10 has to come out of the function at some point, meaning at some point I have to be at 8, at some point I have to be at 3, at some point I have to be at 9, because I'm continuously going from 2 to 10 on the y values. And that someplace, let's say C, at some C value, I'm going to get every number in between 2 and 10. The most important part of this theorem is that we have to be talking about a continuous function on a closed interval. So the very first thing you're going to check is, are we looking at a function that's continuous on the interval that we're being specified? Then you're going to check, okay, what are my two outputs? And is the number that I'm looking for between those two values? Let's look at some practice problems. So the first thing I notice about number 1 is this is a quadratic, so I'm just going to note that f is continuous. And it's continuous on this interval, but it's really continuous everywhere. The next thing I need to check is I need to check to see what's happening at the end point. So what is happening when f is 5 and what is happening when f is 0 on the endpoints of this interval. So if I plug 5 into this function, I'm going to get 25 minus 5, which is 20. If I plug 0 into this function, I'm going to get 0. What that means is between x equals 0 and x equals 5, every single number between 0 and 20 are going to get hit on the y value because I'm going from 0 to 20. 12 is in between 0 and 20, which means that IVT is going to apply. So I'm going to say 12 is between 5 and 20, so IVT applies. Now to find that particular C value, you're just going to say 12 equals your function, x squared minus x. And then we're going to get everything on the same side. 0 equals x squared minus x minus 12. We're going to factor. That's going to give us x equals 4 and negative 3. Now remember, our interval was from 0 to 5. So negative 3, even though it works here, negative 3 isn't going to be the answer. The C value that we're looking for is 4 because 4 is within the interval. So make sure that the function is continuous on the interval we're talking about. Check what's happening at the endpoints and make sure the number that you're looking for is between those two endpoints. And then solve for that value. Let's go ahead and look at number 2. For number 2, we have an issue with continuity here. This doesn't exist when x is equal to 2. And we are looking on the interval from 0 to 3. If we were looking on the interval from 3 to 5, this whole thing would hold and we would still be able to do this. But we're going to say IVT doesn't apply since f is not continuous at 2. Okay, I'm going to move this up so we have a little bit more room to work as we work through our last 2 examples. Number 3. And I encourage you to pause the video. If you're feeling pretty confident, pause the video and see if you can do this on your own. So I'm going to note that f is continuous. It's a quadratic. It's continuous everywhere. I'm going to find the value of the endpoints. F of 3, if I plug in 3, 3 squared is 9, times 3 is 27, minus 4 is 24. F of 0 is negative 4. And we're looking for 0. So I'm asking myself, is 0 in between these two numbers? Yes, it is. So since 0 is between 24 and negative 4, IVT applies. And then I'm going to say 0 equals 3x squared minus 4, and I'm going to solve for x. This is going to give me x squared is 4/3, which is going to give me x equals plus or minus, so if I take the square root of both sides, 2 over root 3. We only care about the positive version in this case since we're looking for the C value between 0 and 3, so that's going to be 2 over root 3. All right, last but not least, number 4. The first thing I notice is that we're talking about a function that's continuous everywhere, so it's definitely continuous on this interval. So we're going to look at what's happening at pi over 3 and what's happening at negative pi over 3. At pi over 3, we're going to get 3 times pi over 3 times cosine of pi over 3 minus 1. And if we simplify this, I'm going to give myself some more room here. This is going to give me pi, those 3's are going to divide out, cosine of pi over 3 is 1/2 minus 1. So this is really pi over 2 minus 1. I'm going to write that as 2 over 2. So this is pi minus 2 over 2. Now, f of negative pi over 3 is going to be 3 times negative pi over 3 times cosine of negative pi over 3 minus 1. This is going to be negative pi. Cosine of negative pi over 3 is also 1/2 minus 1, which I'm just going to go ahead and write as 2 over 2. So negative pi over 2 minus 2 over 2. This is negative pi minus 2 over 2. Now we're looking for a c value that gives us pi. So we need to ask ourselves, is pi between pi minus 2 over 2 and negative pi minus 2 over 2? Well, this is obviously a negative number, so I'm going to look and see if this ever gets above pi, and it's not going to because this is pi, so let's just pretend 3.14 minus 2 is going to be 1 point something, divided by 2 is not going to be bigger than pi. So this is going to be that IVT doesn't apply since C is not between A and B, between f of A and f of B. So let's recap what we learned in this lesson. The first thing that we talked about was continuous functions and one-sided continuity and visualizing or almost pretending to plug in a number to see what's going on. Then we talked about compound functions, figuring out what they are and identifying the interval of continuity along them. And then we wrapped up by talking about IVT and how to check the conditions and find the C value if the conditions are met. So write down any questions you have. I look forward to supporting you on this, and thanks for listening.